Hi everyone, my name is Vaibhav Maheshwari and I'm a software engineer at LinkedIn. I work on streaming technologies like Apache Kafka, Samsa, Brooklin, and Flink. First of all, I would like to thank all of you for listening to this talk. Apache Kafka is the backbone of streaming infra at LinkedIn. The traffic is increasing drastically quarter over quarter, and so are the requirements to replicate the data across the data centers. It is critical to scale the resources based on shifting traffic patterns throughout the day. In the world of chip shortage, it is critical to use the hardware resources efficiently and to reduce the overall operational cost. Last but not least, to detect the anomalies that may impact the replication latencies and take the corrective actions. In this talk, I will cover how are we solving all of these challenges at LinkedIn using Brooklin, which is powered by Apache Pino for real-time analytics. The agenda of this talk is we'll start with the introduction, we'll talk about some of the key concepts. In the next part, we'll talk about the challenges of mirroring with Brooklin Mirror Maker. In the next part, we'll dive deeper into the solution and some of the key results. And finally, we'll talk about the contributions of this feature. Let's get started. What is Brooklin? Brooklin is a distributed service that intends to stream data across various heterogeneous sources and destinations. Brooklin can simultaneously power hundreds of data pipelines across different systems. It can also be extended for new sources and destinations. Brooklin can also be used to stream Change Data Capture Event or CDC from the data stores. Brooklin Mirror Maker is another functionality of Brooklin which is used to mirror the data across the Kafka clusters. Data stream. Data stream consists of a source, a destination, an allow list regex, and its functionality is to stream the data from the source to the destination cluster. In this example, the red data stream represents the data flowing from metrics in data center A to aggregate metrics in data center B. Similarly, the orange data stream represents the stream of data from metrics in data center A to aggregate metrics in data center A itself. So let's go into the anatomy of a Brooklin data stream. Data stream source. The source to consume from, for example, Kafka topics. Kafka topics. It's a category to store particular stream of data. In this example, there are 3 Kafka topics, orange, green, and red. A Kafka topic can have multiple partitions. The height of each of these partition blocks shows the throughput load required for those partitions. Data stream task. It's a unit of work associated with the data stream. A task processes subset of partitions. So in this example, there are 3 tasks, green, yellow, and orange, task 1, task 2, and task 3, with their own partitions, assignments. Partition assignment is a group of unique partitions a task is responsible to mirror. So in this example, the height of each of these blocks of task 1, task 2, and task 3 represents the throughput load required from these tasks. And the horizontal dot shows the maximum throughput a task can support. Let's talk about the Kafka mirroring use cases. First of all, it's required for aggregation, which helps with analytics of your data if your data is spread across multiple data centers. Similarly, for access, in case you have different security domains and your user has only access to certain domain. Another important use case is fault tolerance. In case of multiple data centers and one of your data center goes down, how do you recover the disasters? In that case, mirroring helps with recovery of the outages. Another use case is cloud migration. In case you have a deployment which is both on-prem and cloud, mirroring the data from on-prem to cloud and vice versa is very useful. Let's talk about the Brooklin scale. It's approximately 7 trillion plus messages every day to replicate across the Kafka clusters. In terms of topic partitions, there are 100,000 topic partitions, and to do all of this replication, Brooklin requires approximately 2,000 Brooklin hosts. Let's go into the next sections of what are the challenges with Brooklin Mirror Maker. The first challenge is the throughput load more than what a task can handle. So each task, based on its CPU and I/O, has its own limitation on how much it can process, which is represented by the horizontal dot of the max throughput from a task. In this example, you can see, based on the partition assignment done, the yellow task requires a lot more throughput than what it can support. This results in message delivery latencies, and we miss out on our delivery SLAs. The second problem is there is no insight to predict the task count. Because you are missing out on delivery latencies, you end up reserving extra tasks, because of which you will not have delivery delays, but you end up using additional resources. This results in wastage of your resources overall. On the other spectrum, you may end up reserving less, and you might have message delivery latencies and missing of SLAs. All of this results in a lot of manual human toil and requires human intervention at times. Another challenge is no adaptation to changing traffic patterns. As we talked earlier, the height of the partition represents the throughput load, and this particular assignment was done based on the current load pattern, which is balanced in terms of partition count. But during your peak traffic, the load changes across the partitions, something like this, where the orange ones represents increase in the byte rate, and the yellow one represents the decrease in the byte rate. So the task 1 assignment, which was earlier well balanced in terms of the throughput load, suddenly requires a lot more than what it can really support, while task 3 has become more underutilized. So there is no adaptation to any changing traffic patterns because it's all balanced based on partition count. Another problem is to identify the offending topic partitions. There are two possible scenarios. The first is, suppose you have traffic flowing fine based on the partition, but suddenly over the time, you have increase in your Kafka topics, and the overall requirement is a lot more than what each of these partitions can handle, and you have not increased the topic partitions. In that case, you will have an increase overall across the partitions. Or you have written a very poor partitioning logic, which results in a skewed traffic patterns across your topic partitions. In both these scenarios, you will have the topic partitions requiring a lot more load, which a particular task may not be able to handle and is more than our SLA. So in that case, it's critical to identify these topic partitions and take the corrective actions. So what is the root cause of all of these problems? The partition distribution is balanced, but is balanced based on count, which means all the partitions get an equal weight of 1, which is not realistic. Every topic may have a different load. Based on how the partitioning logic is written for the Kafka topics, they may also have a different load. So the count-based distribution does not guarantee the balanced load. It does not even consider the partition load while doing these assignments. And it may result in underutilization of your task if you have reserved extra. So how are we solving these challenges? We clearly identify that the partition assignment based on count is not working for us. And for that, we need the partition assignment based on the throughput load so that we get a well-balanced partition assignment. And to do that, we need 3 big pillars. The first pillar is to understand the throughput load, and for that, we need to generate our partition-level metrics. This is where we use our real-time analytics to understand the real-time traffic and act as our source of truth. The second part is to utilize this information and to make a proper task estimation and to do throughput-based partition distribution. This helps with smart rebalancing and optimization based on the traffic changes. And the last pillar is the monitoring service, which helps with automation and dynamic adaptation to the traffic. To generate our source of truth, we have built a service named Partition Metrics Provider service, which generates the partition-level metrics. We are not calculating any of this information on our own, but relying on all the existing services. So, for the first pillar, we are generating the partition-level metrics using the Partition Metrics Provider service, PMP. For the service, we use 3 open source products: Cruise Control, Apache Samsa, and Apache Pino. We'll look into each of these particular sections on how they are contributing for the real-time analytics in the next slides. So let's start with the first component, Cruise Control. Cruise Control is an open source distributed service that monitors the Kafka clusters and automatically adjusts the resources based on the predefined goals. It could mean addition or removal of brokers, moving the partition from one broker to another, identifying a slow broker. While monitoring the Kafka cluster, it emits both topic-level and partition-level metrics. The partition-level metrics contains incoming byte rate, incoming message rate, the disk usage, leader and the follower broker information. These metrics are emitted at a configured rate, say for example 5 minutes. Cruise control is heavily used at LinkedIn to monitor all of its Kafka clusters, which means we already have all of this information lying around in our Kafka topics. Cruise control has enough adoption across the industry, and some of the big players apart from LinkedIn using this service are Cloudera, Amazon MSK, Banzai Cloud, and Bloomberg. So cruise control helps us with ensuring the balancedness of the Kafka brokers and emission of the partition metrics. But it emits all of these data in its own serialized format, and it's present in separate Kafka topics in separate Kafka clusters. And that's where we need our next component, which is Apache Samsa. Apache Samsa is another open source distributed data pipeline engine that allows ingestion, transformation, and emission of data from different sources and destination. Apache Kafka, Azure Event Hubs, and Azure Blob Storage are some of the examples of data stores. So in this case, we ingest the data from multiple Kafka topics based on their serialized format. Apache Samsa filter the records and remove the really low throughput Kafka topic partition results. It transforms the records into Avro format and then produce it to one Kafka topic. Why does it do a transformation to Avro format is we'll see in the next slide. And that's where we get the next major piece, which is Apache Pino. Apache Pino is an open source real-time distributed OLAP data store that delivers real-time analytics in really low latency. Apache Pino understands various data formats, but we have enforced the Avro format at LinkedIn to avoid the operational overheads. And this is the reason why Samsa does the transformation from its own serialized format to Avro. Apache Pino is highly available and has a really high data rate ingestion capacity. Most importantly, it has the data available immediately to compute the queries upon real-time ingestion. It gives supports to filter results based on column fields, for example, data center, cluster, topic, partition, and most important of all, timestamp. So we can go and look in any last 1 hour, how was the data pattern, or in the last 1 day. It also gives efficient computation aggregations like max, min, average, which helps with doing all of these computations. It also has long data retention, and it gives support for SQL queries, which makes it very easy to query Pino and get the data out of it. Real-time operation metrics analysis, ROMA initiative with LinkedIn Pino, is used for this solution. So feel free to contact the Apache Pino team at LinkedIn if you're interested to know more about it. So now we have all of this data present in Apache Pino, which has exposed us in REST endpoint where we can make a SQL query and get the real-time data as it's ingesting. So in this slide, we'll see how some of the SQL query look like. It's a very simple SQL query with selects topic partition, some of the components like average of the byte rate, average of the message in rate from the Pino table, filtering based on the data center, filtering based on the timestamp. In this example, it's filtering for the last 1 hour and see how the data looks like. It's also filtering based on the cluster name here, and then grouping all this information to get the average and to figure out which are the top topic partitions having the most throughput load. One more thing that I would like to mention at this point is Apache Pino gives an amazing integration with Power BI, which helps us with visualizing our data. So now that our first pillar is ready, let's dive into the next thing on how Brooklin is utilizing this information. In this slide, we'll talk about data stream task estimation and the partition assignment. The blue block on the left side represents the Brooklin cluster, which has a leader coordinator and other Brooklin nodes. The job of leader coordinator is to do the partition assignment and the task assignment. The Brooklin nodes receive the assignments and then it runs those Brooklin tasks. We have a metric system which is collecting the metrics from all the Brooklin clusters and constantly emit it. We also have Kafka topics lag monitor, which is looking into the consumer groups and figuring out which particular topic partition has how much lag. As we discussed in the previous slide, the Pino block has the Partition Metrics Provider service, which is an endpoint. And we also have a monitoring service, which is looking into all of these components. So all the Brooklin node periodically emit the metrics. The metrics may include how much data it has processed, what's the byte it has, how much byte it has processed, how many records it has processed, for which topic partition, which gets collected into the metric system. The monitoring service periodically polls these Brooklin metrics. It also periodically polls the lag status from the Kafka topics lag monitor. The monitoring service is also making a periodic call to Pino service and getting to identify the topic partitions with high throughput rate. Now that monitoring service has all of this information, it periodically determines the need for rebalance for a particular data stream. If it identifies that there is a need for a rebalance, it triggers the rebalance for a data stream to the leader coordinator of the Brooklin cluster. At this point, the leader coordinator makes query to the PMP and get the partition metrics information. Once it has all the partition metrics information, it does two jobs. The first thing is to do a task estimation. While doing task estimation, it considers certain changes in the traffic patterns, and it also keeps buffer just in case there is a glitch in the network. Once it completes the task estimation, it does the partition assignment based on the throughput for each of these partitions. It applies the bin packing algorithm and ensures that the throughput rate remains balanced across these tasks. We don't try to balance it perfectly, but even if the 90% is balanced, it's good enough in the overall results. So now that the partition assignment is completed, let's see how the result looks like. In this new diagram, you can see all the partitions are distributed based on their weight rather than on the partition count, and each of the task height is less than what the max throughput can support. In this case, the task estimation is also done with additional buffer reservation. One of the peculiarity of this distribution is it supports uneven partition count, and it gives fairness to all the topic partitions because each of these tasks has enough resources to process the byte rate coming in these partitions. Let's look into the key results of this feature. To make a correct benchmark, we have created this certification setup. The certification setup has a source Kafka cluster and a destination Kafka cluster in two different fabrics. We have a Brooklin service running in a control cluster and a candidate cluster. The Brooklin service runs on the destination fabric, which means it's going to do remote read and local write. It's going to read the same Kafka topics, but write to different Kafka topics at the same destination Kafka cluster. In terms of hardware, both the clusters have the same configuration. The only difference is the control cluster is running the algorithm without the load balancing, versus the candidate cluster is running the algorithm with load balancing. So this is the first graph that we saw as part of our experiment. This graph represents the inbound network rate of how much traffic did we saw at a host level. Each line here represents a Brooklin host. The first top graph is the one without the load balancing feature, versus the second one is with the load balancing feature. As you can clearly see, the deviation in the inbound network rate for the control cluster deviates from 30 Mbps up to 80 Mbps, versus in the candidate cluster, there was minimalistic deviation across all the hosts. So what we infer from this is the candidate cluster assignments are well balanced as compared to the control cluster. The other important feature about this graph is at around 10 o'clock is when we have a load testing running, and the candidate cluster was able to scale up based on the load, versus the control cluster had no changes. This helps in understanding that with the load balancing and the correct monitoring service, we were able to automatically scale up our resources in the candidate cluster, which was not the case with the control cluster. Now that we looked in terms of inbound network rate, let's look into the processing of the event bytes. This graph represents the total events uncompressed byte processed rate. Again, each of the line represents a Brooklin host. As you can clearly see in this graph as well, the byte processing rate had a lot of deviation in the control cluster as compared to the candidate cluster. So with the certification setup, what we realized is the load balancing algorithm is working very nicely for us as compared to the control cluster and is also solving the challenges that we were seeing in our existing setups. Let's talk about the final block of this talk, the contributions of this feature. The first capability that it provides is the partition distribution based on throughput rather than based on the count. The other important functionality is it allows to have high throughput for each of these data stream tasks. With the high throughput, we are able to achieve a lot more hardware utilization and better efficiency. Task count prediction, we have clearly seen reduction in the manual toil, which is very challenging. Another important functionality it provides is to dynamically adapt to changing traffic patterns. Suppose you have a cloud-based deployment. In that scenario, you only pay for the peak traffic time for the additional resources, and other than that, you can auto-scale based on the traffic patterns. Because of the real-time analytics, we are able to identify the offending topic partitions and take corrective actions. And also, in case you don't have a dynamic resizing of your cluster, it gives enough functionality that you can set up alerts to resize the static cluster. Let's talk about the improvements once we did the deployment. We saw a 90% reduction in message delivery SLA misses. In terms of hardware reduction, we were able to reduce 30%, and that's a conservative number. It also involves that we kept enough reserves for the changes in the upcoming quarters, and also in case there is a network outage and we have to catch up for all the messages from the backlog. In terms of offending topics, we were able to identify 50 plus topics and able to take corrective actions on them so that they don't impact the overall message delivery SLAs. So this feature is running in Brooklin clusters at LinkedIn for several months, and we have seen a huge reduction in our overall manual toil. We can clearly say that real-time analytics has enabled Brooklin to do smarter replication, efficient resource utilization, and huge reduction in manual toil. Integration with real-time analytics is playing a significant role in managing any large distributed service. And with this, we come to the end of this talk. I would like to thank all of you again for listening to this talk. If you are interested in knowing more about this, feel free to contact me on my LinkedIn or Twitter handle. Thank you.